Hello again, young adventurer. I see you've successfully navigated your first two trials and are eagerly anticipating the next part of your journey. Well, what are you waiting for? Follow me. Welcome back. We hope your journey so far has been rewarding. As we noted in the previous part, this stage of your journey is the most challenging. But worry not, my friend, for once you understand how the Bayesian philosophy can be applied to structural time series, you will be ready to apply it to data. In this part of the adventure, we will see how the Bayesian framework can be applied to structural time series. We first discuss Bayesian structural time series when we do not have a regression component. This includes the prior distribution of our parameters and how to obtain the posterior distribution. We only briefly cover this, as our main focus is the case where we do have a regression component. Again, in the case where we add a regression component, we will discuss the prior distribution and obtaining the posterior distribution. Assuming we don't have a regression component in our model, for example, the local level model, then our parameters are the variances of the error terms. So we would need to specify a distribution for, say, sigma squared epsilon. To keep things simple, we won't discuss a particular prior here. Just remember, the parameters in structural time series models are the error variances, and we would need to specify a prior for each. The posterior distribution is obtained numerically. The Kalman filter and Kalman smoother algorithms are typically used in state space time series models, along with Markov chain Monte Carlo sampling. When we do have a regression component, we use what is called a spike and slab prior. We will consider our regression coefficients fixed through time, because otherwise they could be added as an additional state component. The spike in spike and slab regression is a prior that specifies a positive probability for each regression component being equal to 0. The slab is the prior for each of the regression coefficients that are non-zero, and also the prior for the variance of the error term. This should become more clear as we discuss each of these in more detail. To understand the spike component, we will need a bit of setup notation. Suppose we have a vector gamma, where each component, gamma k, is equal to 1 if beta k doesn't equal 0, and is 0 otherwise. Here, beta is the vector of regression coefficients. Further, we use beta gamma to denote the subset of the vector beta corresponding to the gamma k's that are equal to 1. For example, if gamma 1 and gamma 2 are equal to 1, and all other components are 0, then beta gamma will be the vector of beta 1 and beta 2. The prior distribution we use for gamma is an independent Bernoulli prior. This means that for each component of gamma k of gamma, pi k is the probability that gamma k is equal to 1, and thus beta k is included in the model. We will discuss how to choose the pi k's shortly. Along with specifying our spike prior, we need to specify the slab prior. Again, we need a little notation to start with. For a symmetric matrix omega inverse, we let omega gamma inverse denote the submatrix whose rows and columns correspond to the indices k, where gamma k is equal to 1. This is the same idea as with beta gamma. The slab prior is shown here. It says that beta gamma, given sigma squared epsilon and gamma, follows a normal distribution with a mean vector b gamma and covariance matrix sigma squared epsilon omega gamma. As is often done in Bayesian statistics, to ease calculations, we specify a distribution for 1 over sigma squared epsilon instead of sigma squared epsilon directly. This distribution is gamma distributed with parameters v over 2 and ss over 2. The parameterization for the gamma distribution here is the shape rate parameterization. For this prior, we need to specify b, sigma squared epsilon, omega inverse, v, and ss. But before we do, we want to note the full prior. The full prior is the product of the 3 individual priors we just discussed. We don't write it out in detail here because it might look a bit intimidating, but you are certainly welcome to do so yourself if you're so inclined. Now that we know what the priors are, let's discuss how we choose specific priors. The hyperparameters for sigma squared epsilon are v and ss. We can think of these as sort of like a prior sum of squares and a prior sample size. In the BSTS package, this boils down to selecting an expected r squared from the regression and an expected model size. The default values are r squared equals 0.5 and v equals 0.01. For the pi k's, we specify the probability that beta k should be non-zero. For example, if we are very certain beta 1 should be in the model, we could specify pi 1 to be 0.95. If we don't have any previous knowledge as to which regression components should be included, we could set pi k to 0.5 for every k, which is the default in the BSTS package. Choosing the covariance matrix, omega inverse, is based on the model matrix X. BSTS sets omega inverse to be k over n times x transpose x for a specified value of k. This essentially reflects our prior knowledge on how close beta is to the prior mean vector b. The default value in BSTS is k equals 1. That takes care of the prior, so now we are ready to move on to the posterior. Again, we need a little notation to set things up. Let z star t denote the observation matrix zt with beta transpose xt set to be 0. Let y star t be the data yt with z star t transpose alpha t subtracted out. And finally, let y star be the vector containing y star t for t equals 1 to n. Then the posterior distributions of beta gamma and 1 over sigma squared epsilon are as follows. Beta gamma given sigma epsilon, gamma, and y star follows a normal distribution with mean vector beta tilde gamma and covariance matrix sigma squared epsilon v gamma. Additionally, 1 over sigma squared epsilon given gamma and y star follows a gamma distribution with shape n over 2 and rate ss gamma over 2. The parameters of each of these particular distributions are listed below. And the posterior of gamma is listed here. To obtain a sample from the posterior distribution, we use a combination of a stochastic Kalman smoother and a Markov chain Monte Carlo algorithm. The algorithm is called stochastic search variable selection, which is a Gibbs sampling algorithm. Note that you don't need to worry about implementing this yourself, as the BSTS package will do it for you. Congratulations! The most strenuous part of your journey is over. Now that you understand the mysterious beast that is Bayesian structural time series, you are ready to complete your journey by learning how to implement what you have learned so far.